Hi, this lesson is about trigonometric equations. So a trigonometric equation that has a trigonometric function in it. So in its most basic form, you have some trigonometric function equal to a constant. And when you're solving it, you're basically looking for the angle, which could be called theta or x, or whatever you really want to call it. But they can get more complex, but we'll start with the basic ones. So for example 1, I want to find all solutions to the equation sine of theta equal to negative root 3 over 2 in degrees on the interval from 0 to 360 and in radians from 0 to 2 pi. All right, so you should recognize these numbers, root 3 and 2, as one of those special triangles. And it's actually a 30, 60, 90 triangle. So if this is sine of theta, where your theta is here in this corner here, then you would have root 3 here and 2 here, and this other side would be 1. And the angle that corresponds to that is a 60-degree angle. 60 degrees is the same as pi over 3 in radians. Okay, but that's in quadrant 1. But here you're told that the sine of theta is negative root 3 over 2. Where is sine negative? Sine is negative in quadrants 3 and 4. In other words, where the y values are negative. So in order to get your quadrant 3 angle, you basically have to do 180 plus 60 to get 240. And to get your quadrant 4 angle, you have to do 360 minus 60 to get 300. You would do something similar to find it in radians. Remember, 60 degrees is pi over 3. So to get into quadrant 3, you would do pi plus pi over 3, and that gives pi over 3. And to get into quadrant 4, you would do 2 pi minus pi over 3, which is equal to 5 pi over 3. You could have also taken the angles, the 240 and the 300, and converted them to radians. Remember to convert from degrees to radians. You take your degrees and you multiply by pi over 180, and that gives you radians. So, for example, if you did 240 times pi over 180, well, you could divide 240 and 180 by 60. That's the greatest common factor, so that gives you 3, and that gives you 4. So that's equal to 4 pi over 3. So you get the same result that we got here. So there's more than one way to come up with your answers. All right, so here's another example. We want to find all solutions for the equation tan of theta equal to 1 in degrees on the interval from 0 to 360 and in radians on the interval from 0 to 2 pi. All right, so this should also be a familiar number to you because tangent of an angle is equal to 1 when the angle is 45 degrees. So, and that's because the adjacent and opposite side are equal. So when you take the tangent, which is opposite over adjacent, then you get root 2 over 2, which is 1. Okay, but tangent is positive in 2 quadrants. It's positive in quadrant 1 and in quadrant 3. So your quadrant 1 answer is right here. It's 45 degrees. And your quadrant 3 angle would be 180 plus 45, and that's where we get 225. You would do something similar for radians. So 45 degrees in radians is pi over 4. Again, you can do that. You might have memorized this already, or you can multiply 45 by pi over 180 as we did above. You get pi over 4. And then similarly, you can find this value by doing pi plus pi over 4, and you get that the other radian value is 5 pi over 4. All right, so let's move on. I want to find all solutions of cosine of theta equal to 0.28 in degrees rounded to the tenths place on the interval from 0 to 360 and in radians rounded to the thousandths place on the interval from 0 to 2 pi. Well, 0.28 is certainly not one of those special triangles that we should know. So in this case, you do need a calculator. So when you use your calculator, you're going to use the cosine inverse function. And to solve for degrees, make sure you are in degree mode first. And so being conscious of your mode is really important with these problems, or you will not get the correct answer. So when you enter that into a calculator, it will only give you one result, which is this one here. It's 73.7 degrees rounded to the 10th place. That's in quadrant 1. But we know that cosine is positive in 2 quadrants. That's in quadrant 1 and 4. So in quadrant 4, you would do 360 minus 73.7 degrees, and you get 286.3 degrees. To find the second set of values here, you have to now be in radian mode. And so switch to radian mode and then do cosine inverse of 0.28. It will give you 1.287 when you round to the thousandths place as indicated above. And then similarly, you would derive the second result by doing 2 pi minus 1.287 to get 4.996. All right, so we're moving on. This time you want to solve the cosine of theta equal to a half. All right, well, we're back to a triangle that should be familiar to you. So this is, again, a 30, 60, 90. So when it's cosine a half, this would be 1 over 2, and this one here would be root 3. That's when this angle is 60 degrees. And 60 is the same as pi over 3. Okay, so this time we're only going to present our answer in radians. And so pi over 3 is one answer because cosine is positive in quadrant 1 and 4, as we mentioned above. And then in quadrant 4, we get this answer, 5 pi over 3, by doing 2 pi minus pi over 3 to get 5 pi over 3. Okay, but notice that this time I didn't give you restrictions like I did above, where I said 0 to 360 or 0 to 2 pi. So that means you have to present your answer for every possibility, keeping in mind that the cosine function oscillates up and down forever and ever and goes through one period in between 0 and 2 pi units. You could also think of it in terms of the unit circle. It keeps going around and round and round. So in order for us to represent that, you say that theta is equal to pi over 3 plus 2k pi, where k is an integer. Now, what's an integer? An integer is the set of numbers. So there'll be numbers, they could be negative, positive, or 0, but you won't have fractions or decimals. So this is an example of the set of integers. The dots mean that they go on and on towards negative infinity and infinity. So for every 2 pi units, starting at pi over 3, you end up on the same place in the unit circle, or you get the same value along the graph. The same is true for 5 pi over 3. Add 2k pi units, and you end up at every possibility where cosine of theta is 1/2. Okay, so here's another one that should look familiar. We want to solve for all possible values of theta where sine of theta is negative root 2 over 2. So again, those numbers should look familiar. This is a 45-degree triangle. So this is a root 2, 2, and this one's also root 2. Okay, so, and we know that 45 degrees is pi over 4. We just did one with 45 degrees. Okay, but this time it's negative, so 45 degrees isn't going to work. That's in quadrant 1. Sine is negative in quadrants 3 and 4, so we have to present our solution in quadrant 3 and 4 using our reference angle of pi over 4. So how do we get 5 pi over 4? Well, that's just pi plus pi over 4 in quadrant 3. And this one here is 2 pi minus pi over 4, and that's in quadrant 4. And again, if we want to represent it for every possibility, every oscillation of the graph or every turn around the circle, then we have to add 2k pi units to both of those angles to get these infinite number of solutions, 5 pi over 4 plus 2k pi, or 7 pi over 4 plus 2k pi, again, where k is an integer. So for every value of k, that means another rotation around the circle. When k is negative, that means you're going clockwise. When k is positive, that means you go counterclockwise around the unit circle. All right, so here's another one. We want to solve for all possible values of theta for tangent of theta equal to 2. And we want to round these answers to 2 decimal places. And again, we'll present it in radians. So this would be in radian mode. We don't know a special triangle that has 2 over 1. So that comes from here. 2 over 1 as opposite over adjacent. So we need a calculator. So keep in mind that tangent is positive in quadrants 1 and 4. So whatever answer you get, you're going to have to then make sure it's in the appropriate quadrant. So we're going to take tan inverse of 2, put the calculator in radian mode. That will give you an approximate value of 1.11. 1.11 is in quadrant 1. So this is 1.11. And the reason I know that is because this is 0, and this is pi over 2, and pi over 2 is about 1.57. So 1.11 is an acute angle. All right, but here we can handle tangent a little bit different than we did sine and cosine in the previous examples, where we had to present 2 different answers and then add 2 pi k units to it, because tangent has the same sign in opposite quadrants, so in quadrants 1 and 3. So if I add pi units to 1.11, then you end up in your quadrant 3 angle. And if you add another pi units, right, then you end up back in your quadrant 1 angle. So in fact, your theta is equal to just 1.11 plus k pi, where again, k is an integer. It's a set of integers. It kind of is represented with that z with the double line on the angle. Okay, let's move on. So here we want to solve for all possible values of theta for 2 cosine squared of theta minus 7 cosine of theta plus 3 equal to 0. All right, so this is a trigonometric equation that looks a lot like a quadratic equation. So you can think of this as 2x squared minus 7x plus 3. And if you were to factor that, well, you would be looking for 2 expressions that will give you 2x squared. So that's 2x and x. And then you would need 2 expressions that would give you 3 in the last position. And keep in mind the signs. The last term is positive, middle one is negative. So 1 and 3 are going to be my choice, but you have to figure out where to put it. So if you put 3 here and 1 here, both negative, that will give you negative 6x and negative x. Negative 6x and negative x gives you the negative 7x. So we're going to apply that to our trig function here below. So instead of 2x minus 1, I have 2 cosine theta minus 1. And instead of x minus 3, well, I have cosine theta minus 3. Then we set each factor equal to 0. And you get that cosine theta is a half. So I kind of skipped a step here when you solve this one. Cosine theta is a half. And the second one is cosine theta is 3. Okay, so let's deal with cosine theta is a half because we've actually worked with this number before. 1/2 is a 30, 60, 90 triangle. And when cosine is equal to a half, that means that the angle is 60 degrees. 60 degrees is pi over 3. So, and that's in quadrant 1, which is good because cosine is positive in quadrant 1 and in quadrant 4. So in quadrant 1, you get this result, pi over 3 plus 2k pi, or 2 pi k means the same thing. That means that you keep going around and around and end up in quadrant 1. And in quadrant 4, well, that's just 5 pi over 3 plus 2k pi. Okay, but we still had this other factor, cosine of theta is equal to 3. Cosine of theta equal to 3 has no solution. And if you actually plugged it into a calculator, did cosine inverse of 3, your calculator should give you an error. And that's because, if you recall, so this is just a reminder of something we did in the last chapter that we worked on. Recall that the domain for cosine was all real numbers, but I did have a restriction on the range. The range was from -1 to 1. So saying that cosine of theta equals 3, that's impossible. Cosine of theta can only have a value between -1 and 1, including those two numbers. Okay. So let's go on. We want to solve for all possible values of theta in radians for secant squared of theta minus secant of theta minus 2. This is also a quadratic equation. And if you thought of it in terms of x squared minus x minus 2, then you would factor that as x minus 2 and x plus 1. That would give you the factors that correspond to that quadratic equation. So think of x as your secant. So when you factor, you get what you see here. Secant of theta minus 2 times secant of theta plus 1 equals 0. All right, so we set this equal to 0. Each factor equal to 0, you get this result. Secant of theta equals 2, and secant of theta equals -1. All right, so it's easier to think these through in terms of sine, cosine, and tangent. And if we needed a calculator, you'd have to do that anyway. So secant is the reciprocal of cosine. So if secant of theta is 2, then cosine of theta is a half. And if secant of theta is -1, then cosine of theta is also -1. The reciprocal of -1 is just itself. So we're back to familiar numbers. We don't need a calculator at all. Where is cosine equal to a half? Well, we just discussed this actually a couple times in this lesson. Cosine of theta is equal to a half at 60 degrees, and 60 degrees is pi over 3. So in quadrant 1, theta is equal to pi over 3 plus 2 pi k. And in quadrant 4, which is the other quadrant where cosine is positive, you get 5 pi over 3 plus 2 pi k. But now we have to deal with this other angle here, cosine of theta equal to -1. Remember, cosine has a value of either 0, 1, or -1 on the quadrantal angles. And it's equal to -1 at pi. So as a reminder, if this was your unit circle, this was the point 1, 0. This is the point 0, 1. Here it's the point -1, 0. And here it's the point 0, -1. So here you're at 0 radians. Here you're at pi over 2 radians. This is pi. This is 3 pi over 2, and then you return back to 2 pi. Okay? So the x value is the cosine value, and the y value is the sine value. It's the sine value. So where is the x value equal to -1? That's right here, and that has a value of pi. And again, because you can keep going around and around this unit circle and ending up in the same place, if you start at pi and keep adding another 2 pi units or subtracting if k is negative, that means you're either going counterclockwise or clockwise around the circle and ending up in the same position where pi is. So we get theta is equal to pi plus 2 pi k. So you have 3 possible solutions, actually an infinite number of solutions because of the 2 pi k that's being added to them. But your starting values were pi over 3, 5 pi over 3, and pi. Okay, so here's another one. This one works out to be a quadratic equation, but there is some substitution that you have to do. It's a little bit more complex than the other two. So we have cosine of theta plus 1 equals sine of theta, and we only want to state the solutions on the interval from 0 to 2 pi. So that means there's a restriction in terms of what we need to find instead of all possible values. Okay, so here we're going to apply a trick, and the trick is to square both sides. It's actually difficult to solve a trigonometric equation when you have more than one trigonometric function in it, like we do here. We have cosine on the left, sine on the right. So I'm going to square both sides. And when you square both sides, on the left, you have to FOIL. And when you FOIL, you get cosine squared of theta plus 2 cosine of theta plus 1. And then on the right side, you get sine of theta squared is sine squared of theta. Remember, these two notations mean the same thing. All right, so now is when I'm going to do my substitution. Again, because I have sine and cosine in my equation, I'm going to get rid of actually the sine squared. So remember the the Pythagorean identities, and this was the first one we learned, is that sine squared of an angle plus the cosine squared of an angle is equal to 1. If I were to solve this for sine squared, that means I'm going to subtract cosine squared over to the right. So then I get sine squared of theta is equal to 1 minus cosine squared of theta. So the sine squared of theta in my equation right here gets replaced with 1 minus cosine squared of theta. So now I only have cosine in my function. And I definitely have a quadratic equation because I have a cosine squared on the left and on the right. So I'm going to set the whole thing equal to 0 in the next 2 lines. So here I added cosine squared to both sides, so to move it from the right to the left. And then here I subtracted 1 from both sides so that it's in standard form equal to 0. So now I'm ready to factor. So this one only has 2 terms, so we're not factoring it the way we did above as 2 binomials. We're just going to pull out the GCF first. So I factor out 2 cosine theta. That leaves me with cosine theta plus 1 being multiplied by that. Set each factor equal to 0, which is what you see on the next line. 2 cosine of theta equals 0, and cosine of theta plus 1 equals 0. So that means that cosine of theta is equal to 0 when you divide both sides by 2. And here cosine of theta equals -1 when you subtract 1. So this is back to our quadrantal angles. Cosine is equal to either 0, 1, or -1 on the quadrantal angles. Where is it equal to 0? It's equal to 0 at pi over 2 and at 3 pi over 2. And it's equal to -1 at pi. And again, because I'm only interested in solutions between 0 and 2 pi, as we set up here, then that's all we need to do. Just list those 3 answers. Okay, so we have a few more. This is another quadratic equation. So we want to solve 2 cosine squared of theta minus 1 equal to 0. And again, I'm giving you a restriction, this time in terms of degrees, from 0 to 360. All right, although it's a quadratic equation, I'm actually not going to factor, although you could factor this one. It's, you can't factor this one. I'm actually going to use the square root method. So I'm going to add 1 to both sides, which I did here, then divide by 2, which I did here. So you have cosine squared of theta equals 1/2. So now I'm ready to take the square root of both sides. When you take the square root, don't forget that you to put the plus or minus in front of the answer. So cosine of theta is equal to plus or minus the square root of 1 over 2. And if you were to rationalize that, well, you get this answer here. Cosine of theta is plus or minus root 2 over 2. And this again should remind you of one of those special triangles, actually the 45-degree triangle. Cosine is root 2 over 2, so the other side is also root 2. So cosine is positive in quadrants 1 and 4. It's negative in quadrants 2 and 3, which means that we have to present our answers in all 4 quadrants using 45 degrees as the reference angle. So quadrant 1 answer is here. Quadrant 2 answer, well, we get that by doing 180 minus 45. That gives us 135. Quadrant 3 answer, that's 180 plus 45. That's 225. Quadrant 4 answer is 360 minus 45 to give you 315 degrees. So again, we don't have to add 360K to each of these because we're not going forever and ever around the unit circle or forever and ever along the graph. We have a restriction here from 0 to 360, so these are your solutions. All right, so here we have another quadratic, a trig function in quadratic form. This time we want to present our solutions in radians because you're told to present x between 0 and 2 pi. So again, you have restrictions. So first thing is put it in standard form, which means set it equal to 0. This one is factorable. So the factors that work are 2 sine of x plus 1 times sine of x minus 1. When you solve each factor, you get 2 possibilities here. Sine of x is equal to negative 1/2, and sine of x is equal to 1. All right, so let's talk about the first one first. Sine of x equals negative 1/2. So first let's consider just 1/2. So when is sine equal to 1/2? That's when this is 30 degrees. And 30 degrees is equal to pi over 6, because we want it in radians. Okay, but where is sine negative? Sine is negative in quadrants 3 and 4. That's where the y values are negative. So how do you get into quadrant 3? Well, we would do pi plus pi over 6, and that's where 7 pi over 6 comes from. And how do we get into quadrant 4? Well, that's 2 pi minus pi over 6, and that's how we get 11 pi over 6. So those are our first 2 answers. Now we have to worry about the other answer here, that sine of x is equal to 1. That's again a quadrantal angle, and if you recall on the unit circle, sine is equal to 1 when your angle is 90 degrees or pi over 2. So you have 3 solutions: 7 pi over 6, 11 pi over 6, and pi over 2. Okay, last one. We want to solve the equation cotangent squared of theta minus 2 equals 5 for angles between 0 and 360, and we're going to round to the, and this is a mistake, we're going to round to the hundreds place. Okay. So we have cotangent squared of theta. We want to isolate that, so add 2 to both sides. That leaves us with cotangent squared of theta equals 5. When you take the square root of both sides, you get that the cotangent of theta is equal to plus or minus root 5. So those are possible answers because the range of cotangent is from negative infinity to infinity. But remember, we think in terms of sine, cosine, and tangent. So cotangent can be written in terms of tangent as its reciprocal. So tangent of theta is plus or minus 1 over root 5. So 1 and root 5 do not represent one of those special triangles. So here you need to use a calculator and make sure you are in degree mode, right? So you have to really pay attention to the directions and what's being asked. So when you do tan inverse of 1 over root 5, that will give you your quadrant 1 angle. But remember, tangent is positive in quadrants 1 and 3. And so this is in quadrant 3. That would be 180 plus 24.09. And then really you're just using your reference angle to get the other two answers. Tangent is negative in quadrants 2 and 4. So in quadrant 2, you're doing 180 minus 24.09. And in quadrant 4, you're doing 360 minus 24.09. So you get all of your answers listed right here. Okay, so you should be ready to try the homework for 7.4. Good luck.